Just slowly restart because of you have already the laptop in front of them. So I wanted to know if any of the download the code, the material, if you have any problem, or just want to have some feedback from those of you who downloaded the material, the code. Okay, so Michael, Yelena, other people who, okay. I mean the runs, because they are connected to the runs already. Yeah. So if you're able to run to launch root, you should be able to open the file. If root works. Yeah. Just open the file. There are some files in the example for your simulation directory. Open the file, just do root, and then we launch the name of the file. By the name of the file. But just to start, so since maybe you are opening, yeah, I just want to say a few words about the code. I mean, I not very democratically decided to start with this, but maybe if we have time, we can also go to the website with the data. So if you like, we can do it later. This code started from an semi-analytical version of the propagation of the cosmic-related hexagram space. So we are talking about what I told you yesterday about the interactions. So the main interactions in the hexagram space, so the implementation of the photon reaction and of the photon space. Okay, so it started from these two papers from people working on the analytical calculations of these reactions. And then I just tried to translate this into a Monte Carlo code, which was a part of my PhD thesis. And then this became was a very handmade, homemade code, but became a paper. And then after that, it was then used in another PhD project. And then now it is used in several applications within the collaboration, also in comparison with other codes. So, you know, I mean, it's like in the experiments, it is always good to have more than one code, more than one application that do the same thing in order to compare one to each other and to see maybe there are differences in the implementation and differences in the inputs. So, for instance, we used at the beginning a very simplified model for the photon interactions, and then we compared to more complicated codes which were using thousands of channels for the photon integration. And then we derived what was the impact of these simplifications in the spectral pattern. And this also contained a paper, and also a paper about the study of the neutrinos, so the effect of all these uncertainties. For instance, in the EDF that Elisa about this morning, so we have 4 implementations of different models of the EDF, and we are able to say what is the effect of using the different EDF models in the propagation of the cosmic rays. So thanks to this, we were able to study the effects of the uncertainties in photonuclei and in astrophysics inputs in the propagation of the cosmic rays. And what is also the impact in the interpretation of the data. So because of this, we could use within the theological collaboration, we could use this code and other codes in official papers of the entire collaboration. So that was very nice for us. So it is a Monte Carlo code, which is written in C++. And basically, it's very, I mean, it's not a very complicated task. So you generate a primary and you follow it from the source, which is some redshift, to the Earth. And travel, so particles travel in a rectilinear way, so there's no magnetic field. If you want to compute that, you have to do more complicated codes, or you have to do it yourself, take SimProp, and then look at the effect on the magnetic. You recalculate the propagation. Of course, it takes, I mean, larger computation time to take into account the deflections, okay? And then there are, I mean, so I could say a lot of characteristics, but I think it's much more fun to try to use it. And then we have a lot of options. We can choose among them. So we can choose basically from starting from the energy, the position, and the mass. So we can choose every kind of isotope from protons up to iron 56 as the primary mass, and then we can follow basically all the propagation. Then we can have different choices of the starting redshift, and different choices, as I said, of the EBL. So these are older papers with respect to what Elisa reported today, but here you see Gilmore and Dominguez that are the most important ones, I think, at the moment, the most used ones. Then the nuclear model. So we start with a very simple case, which is the one in which we have just one isotope per each mass, and then we follow the nuclear chart. We follow basically from iron 56 to protons and neutrons, and we follow just one possibility in the diagonal. This is the basic case. So this is the number of protons and the number of neutrons. While we could also deviate from the diagonal because of choosing other channels, and this was also implemented. So it means that you can go maybe this way, then this, and this, okay, down to, so which means that the reaction that we are simulating is that a nucleus with mass A is interacting with a photon, and then it goes into A minus some number plus that number of nucleons, okay, which can be one or more than one, okay, and this is, I mean, one of the options. And then there is also the option to follow the photoproduction of pions in a continuous way, so that you just assign an energy loss, a percentage of energy loss, or you consider it stochastically, okay? And then there is also the possibility to use, so the code computes also the production of neutrinos and photons. Of course, if you produce the photons and the electrons and positrons, your output will be very, very big. So you have to treat that in some other way. I mean, it's you have to think about some shortcuts. But okay. Then the output is something that is quite interesting, because you can follow the nuclei at each step of the propagation. So it means that you have a nucleus which is generated with mass A, energy E, and at some redshift. And then you are here and you want to see what arrives at Earth. And then you will see at some point A prime at Earth with E prime, and Z is, of course, redshift is 0. So in one of the outputs, you can basically see everything that happens at every step in redshift. So you will see
what is, for instance, the redshift of generation of the secondary particles. So this is the one of the outputs, which is this type, which is called NUC. The other one, which is called summary, contains only, let's say, the A and the A prime. So doesn't tell you where the neutrinos, for instance, are created. So if you want to see exactly where they were created, you have to choose this one. Although in this case, since you still take into account, you still see what are the neutrinos at Earth, you also compute what is the energy. That is very simple. The neutrinos don't suffer any other kind of energy loss than the adiabatic energy loss because of the expansion of the universe, so that you can compute easily yourself. Okay? So you can go back to the Z of the production. Okay. So, so you see there are some example runs that I prepared, which are for 1000 nuclei, like iron 56, for different choices of the source redshift and of the injection energy. So you can open one of them and look at the files, and these are reported in this NUC option. So you will see, so if you open that, we can do it. If you have it, just do it. But we can open one of them. Like, for instance, the one. So you see in the output, in the name of the output contains everything that is needed to recognize your simulation, of course. So you have the number, so the mass, you have the interval in energy, which is this small e and the large e, the big E. Then you have the interval in redshift. So here I choose just everything is the same. So it's a bunch of iron nuclei at 10 to the 20 eV and at redshift 1 that are generated. Okay, then I choose the EBL, and then, okay, this is, I can open this, and then just to see what is inside, you do, so the commands are to be given with the dot, and ls give you the list of trees. So these are organized in trees with some branches, and every branch will contain one of the observables we need. So if we open the NUC tree, and this you can do it with the show option, and then we choose the first entry, which is in this case just the first step in redshift. Okay, and we see what happened in this case. So in this case, we have first nucleus, which is A56 and charge 26, which was originated at redshift 1, which was our choice, and it ended up, it disintegrated in at this redshift. What did it do? This is written in the next entry, but you can have a look already here in the multiplicity. Okay, multiplicity is 1. So what does it mean? If multiplicity is 1 in a photodisintegration, it has emitted, it was disrupted in nucleus which has what mass? 56 minus 1, so 55. And then it has produced either a proton or a neutron. From this, we don't know. Okay? And we don't care about that, right? Because for us, they are the same. So neutron decays in protons, so we don't care about that. So look at the energy. So the energy with which it started is 10 to the 20, and it ended up with this energy, 9.99. Okay? So let's see the next. We do show 1. Yeah. Yeah. Sorry. Or can you see it if I do it just like this? Yeah. No, I don't think it works here. I don't know what to do because I always use it. You don't see it? Even if I am just maybe doing like this. No, even worse. No. Just doing like this. Okay. I don't see it anymore. Okay. So the second entry, it's not the second event, right? For us, this is still the first event. It's still the first primary which has been injected into, okay? So this has generated a nucleus which has A55 and Z25. So this means we have generated one proton because also the charge is different, okay? And then this gives us the origin of the 55, which is exactly the same as the death of the 56, and then the death also of the 55, okay? With the origin, with the energy. Now let's have a look at basically at the proton which has generated. Okay, let's see. This is the proton, of course, mass 1 and charge 1, which was originated at the same redshift at which the 55 was originated, but this actually happens to arrive at Earth. So the end redshift is 0, okay? Look at the energy. So so what is the relation between these three values of the energy at the end? Do you remember what we saw yesterday? What we summarized? Is there a relation between these energies? You can compute yourself, which is quite easy. So in this photodisintegration that happened, we have that the Lorentz factor of the particle is conserved, okay? Right? So if I compute the Lorentz factor of the first part of the 56, which is this one, I will find that it is the same as the two daughters, okay? This simplifies, of course, the things. So now we can try to, or you can, I hope you can, I don't know who is doing that, try to see in total what comes at Earth. Okay, so we have some examples like different redshifts from which we start the propagation and different energies. So we can try to see what is you have to open it by just launching root and the name of the file, which is just this option, root with the name of the file, .root. Does it work? Okay, so now you can I don't know which one you open. Now I'm on the 10 to the 20 with redshift 1. Okay, so we can have a look to some distributions. For instance, this distribution of masses that arrive at Earth if we start with nuclei with the irons at redshift 1. Okay, so we can just draw them. Okay. So we have to take the tree, and one of the branches we want to plot. Okay, so for instance, we want to draw, and then you have to give it with this option. So you can write the minus and the sign, so the arrow basically, and the draw option. And between the parentheses, you write this, and then you can put here the quantity you want to plot. Okay, for instance, we want to plot the mass that arrive at Earth of all the events we have in the end. Okay, what do we have to do? So we have to put the quantity, so the branch we want to plot, and then we have to put some conditions. The first condition is that we want to plot the masses that arrive at Earth. So we have to fix the redshift to 0. So it's just the ones that arrive at Earth. So we have to impose that the end redshift is 0. Okay? And then we have also to impose that the mass is larger than 0. Otherwise, we include all the neutrinos, and now we don't want to. We can also, plot it later. Okay? So now we want to see from our generation of iron particles what kind of masses arrive at Earth if the so we have to impose that the redshift is 0. Okay? Then if we do like this, we obtain an histogram, and then of course we can have to put it in logarithmic scale. Okay? So this means that our iron 56 has generated this distribution of masses, of which, most of them are protons, of course, or neutrons, we don't know. And then there is some kind of distribution of masses that arrive at Earth. So you see, in this case in which we have generated the irons at redshift 1 with energy 10 to the 20, there are no irons that survived. So the disintegration worked in such a way that we are already, quite far, or we are at very small energy, so that the irons do not survive. Okay? And we have lighter masses. Is there any question? Doubt? So in order to change the scale, you have to click on the bar, and it appears this, which is the commands that you can change in the canvas, basically. So you have to set the logarithm. Of course, in this case, it is useful to do it in the y-axis and not in the x-axis, because in the x-axis you have masses up to 56, so it's fine to have it in the linear scale. Okay? So we can ask ourselves, what if we increase the energy of the nucleus? What will it happen? Do you know, can you imagine what can happen if the nuclei will be more or less disrupted, or if we restrict the universe from which we are looking at the cosmic rays? So what we have to keep in mind is the interaction length that we have seen yesterday, which is something like, as a function of the energy, this is a length in megaparsec, but it's something like this, okay? So what we expect is that the larger is the energy. So how to read this first? So the smaller is the length, the higher is the probability to interact. So if we enlarge the energy, what will it happen? That the particles interact more. So if I fix, so now let's do the exercise that we fix the redshift to 1, and then we have seen now the energy, so the logarithm of the energy equal to 20. Now let's keep the redshift still 1 and look at what happens if we have more energetic ions, let's say, okay? So I just open the other file and take the one still at redshift 1, but with the energy 10 to the 21, which is larger. And then I plot the same as before, just, I mean, I did it very fast, so I'm not plotting one on top of each other. But you remember that before we had this kind of enlarged distribution of nuclei at Earth. So now what do we expect? Well, this is just protons. So in this case, what we see is what we expect, right? So we have enlarged the energy of these nuclei so that they are totally above the threshold for the photodisintegration, and they disrupt. They are totally fragmented in protons or neutrons. Okay, you can check the number of the entries, and you see that we are fine. So we have simulated 1,000 iron nuclei with mass 56, and what we find in the end is this number, which is 56,000 of nucleons. So we don't miss any of them. Okay, so it's not a really nice plot. It's just yeah. So I don't know if that if this is clear, considering the fact that we have to keep in mind what is the probability of the interaction. Any question? Mm-hmm. Yeah, so if you want to simulate one, you have to install, you have to do make and so on. And then you can, sorry, I didn't say that because I thought it was easier to use the other simulations, but of course you can do it. So you can run, after you created the executable file, you can run this to see what are the options that I reported before in the presentation. And then you can run it, like, for instance, you do like, I don't know, the proton, like 10 events, okay? And yeah, and then if you leave it without other options, it takes the default one, which is the one depicted with D. Okay, so if I do like this you don't even see it. I mean, it's too fast. So it has created 10 protons with redshift from 0 to 1, which is the option. Okay, so for instance, it has created the first event, which is a proton, you see, because that's what and it has extracted the energy from a flat distribution. It took 1.8 times 10 to the 18 eV at this redshift. So it is propagating and then doesn't do anything. It goes directly straight to the Earth. Why? Why is doing like that? So because this energy is basically not enough to trigger the photo meson production. So the only thing it can do, it can lose energy because of the pair production, which is treated in a continuous way. So it doesn't do anything. It basically solves I mean, it doesn't even solve the differential equation that you need to compute the energy at the Earth, because we have we have solved it once for every time, and we interpolate in the interaction length, basically what we do. Then the second nucleus does the same. It has even smaller energy. You see here, it's 10 to the 17. While the second one does something. So it has, you see, 3 times 10 to the 20 eV, and this is the redshift of generation. Okay, so it's creating a pion. Okay, and then this gives us a lot of other things, photons and neutrinos probably. No, it's pi 0, so doesn't create neutrinos. Okay? So let's see if there is other things. Of course, for this, you have to, so the creation of this is connected to, randomization for choosing the energy and all the other things. In order to have it different from time to time, you have to, you can change the seed number from which you start taking the first event. Then it gives you, you see the muon and the neutrinos, okay? So you see, if it does a photopion reaction, you will have a lot of, you can also reduce this verbosity. There is also, okay, so in the end, it gives you summary, let's say. So of course, in this case, the nucleus type is only 1, and the nuclei, so the protons that reach the Earth are 10, because it's what we generated. It created 48 photons from pi 0 decay, and these are the neutrinos, from which we can also read the energy and the flavor. Okay. So you can do a similar exercise as what we did before. So before we fix the redshift and we changed the energy. You can also, for instance, fix the energy and change the redshift and guess what you will see at Earth. So now that you have the files, you can try yourself. Or we can, for instance, try to simulate. So I just want to show you what is the outcome that you should be able to see. So if you fix, so these are simulations. So this was an exercise that then I put in my thesis, my PhD thesis. So it was very simple, but just to show you which were the tests that I did when I was working on the code. So in this case, for instance, here, the redshift of the source is fixed at 0.02, while in this case it is fixed at 1. For energy at generation. So what you see is that basically if I have the larger energy, which is 10 to the 21, basically I only have, it's the black one. Maybe that you don't see it very well in the screen, but it is just giving protons in both cases. While if I have a closer or a more distant source, these distributions are a bit shifted, due to the fact that basically if you don't have, if your source is closer, you don't have enough space to have all the disintegrations. And then your distribution of masses is more centered towards heavy nuclei. While if you have space, then you can basically you can populate all the cascade in all the places you have. Otherwise, you are stuck somewhere because you reached the Earth too early. Okay, this is a matter of distance in this case. Okay. So another thing I wanted to check, since Elisa told about this this morning, is the effect of the interactions on the EBL. So this is quite trivial to imagine what happens, okay? So we let the CMB to be there, and we switch on and off the EBL. What does that mean? So I'm not sure that you remember, since this is not your field, but basically the interaction length works like this, because here I have the adiabatic energy losses, and here I have the energy losses over the EBL. It means that this reaction happens with photons of the EBL, while this is because of the photons of the CMB. And this is because you have this relation between the energy of the photons and the Lorentz factor of the nucleus. So if this increases, this has to decrease to have the same epsilon prime. Okay? So if I do not have, so if I switch off the EBL, this will look like this. So what should I expect to see if I have that the photon field is less intense? Again, in terms of fragmentation of the nuclei. So if I have a lot of a very dense photon field, or if what happens with respect to the case in which I have a less dense photon field? So if you have some kind of, in the case of the I mean the distribution of the nuclei, just the distribution of masses, that is like this if you have CMB plus EBL. So I have all the photons I can consider. But so what is the case in which I have only, for instance, the CMB? I expect this to be shifted somewhere, right? So let's. So you can look at this by opening. I think. Okay, there are two types. One is this L0, which is the case in which I have only the CMB. It is the case for iron 56, 10 to the 20, and Z equal to 1. And this is only CMB. So if I plot the same, but you can play with that, you can plot, for instance, the distribution of energy. So that is exactly the spectrum that we expect. So if we plot this, we will have a distribution like this. Okay, so with the only CMB, we have, I mean, in this case, this invented case, I mean, it's just for example, I have a distribution which is quite, I mean, shifted towards the iron, so it doesn't disrupt so much. Of course, we have a lot of protons. While, let's open another one. And we open the one in which we have the same, exactly the same quantities, but the L, which is the option for the EBL, is set to 1, and we plot the same. So that's what happens. So in this case, let me, yeah. So in this case, what I have is a much more spread distribution of masses. Okay, so if I have a more intense photon field, the interactions are much more, and then the nuclei are more disrupted. Okay, so this has influence in the in what I expect. So when I fit the spectrum at the Earth, so the last images I've been showing you today are done with, of course, it's not just this raw simulated data, simulated events. You have to fold them with the initial spectrum and so on. But that's what it is. So what we obtain includes the propagation that you have to consider in order to find the parameters at the source. Okay. This is a flat distribution in in energy. So it's not weighted. Of course, I mean that has to be taken into account. It's just as an example. Now we can do it with a simpler example, like with the protons. Otherwise, with the nuclei, it's a bit more complicated to imagine. Yeah. Which, yeah, the ones which had smaller energies then can also interact with the EBL. And then I get that the distribution, the nuclear cascade is more populated. Otherwise, I would be stuck somewhere next to the primary nucleus. Okay. So, are there other questions? So, if not, I just wanted to show some very rough spectrum at Earth with the protons in this case. So with the protons, it's all much more simple to imagine. You don't have any disruption. So you have just energy loss, which is stochastic. But anyway, what we expect is just to be sure that we are on the same page. So we expect as the spectrum at Earth, if you multiply that by E cube, you expect this kind of shape. Yeah. Doesn't. So what is measured? So the flux multiplied by E cube as a function of the energy is something like this. Okay. So of course we should use all the nuclei and so on, but now for simplicity we can try to use the protons. So I just have a very basic macro in root, which is also in your example file, with which I just load the file of the protons. In this case, this is 100,000 of protons. And in this case, I'm not using one fixed energy for the generation. I'm using energies from 10 to the 18 to 10 to the 21 and redshift from 0 to 1. Okay, so I'm basically loading all the branches of the tree that I'm having, and then I want to build this figure, more or less. Let's say just. So what do? I read every entry, and I assign a weight. But what I have, are the protons at the beginning and the protons at the end. So what I see at Earth is this. What I have at the source is what I want to use as a weight for this. Okay. So you remember yesterday we wrote the flux at Earth, which was as a function of the energy. It was an integral, so I have to use the conversion from I have to use the cosmology and so on. But here inside, I have the spectrum at the source. Okay, and then I have the conversion of the energy and so on, and then all the volume. So it is this one that I have to use as a weight for the energy. So then I have the energy at the source and the energy at Earth. So I bin basically the energy at Earth, which is this one. So I'm filling an histogram basically, which has the energy at Earth, and it is weighted by these weights, which is this Q, that takes into account the reweighting, what Jose Manuel was asking, the reweighting at the source, which is power law spectrum, like e to the minus gamma. And then I include also maybe cosmological evolutions and so on, okay? So if I do like this, I can choose the gamma, I can choose the function with which I want to reweight because of the density of the sources, and then I can try to see what comes out. So for this, I just load, I'm not running it because I think it's can give you some errors because it's written in just two minutes, so maybe, but just to show you that in this case I'm obtaining, I mean, of course, it's because of the statistics, it's very rough, but that is more or less the shape, okay? It's quite bad, I mean, it's, you don't have to look at the final part, okay? So let's see, for instance, so in this case, I've been choosing spectral index, which is 2.4, and this is what I obtain. Let's have a look if I choose, for instance, 1.5, just for curiosity, and see what happens. This is the flux multiplied by a cube. So you see that there is a huge change in the spectral index at Earth because of the weight that I give to the initial particles. Okay, so that's what, for instance, this spectral index is what we can fit comparing the expected flux and the measured fluxes. This has also an implication in the secondary particles, okay, which I can show here. With the neutrinos. Okay, so let's see what happens. So this is not normalized. It's, I mean, it's arbitrary units. You would need to put the correct normalization that you do by comparing to the data, basically, at least in this code. But let's see what is the outcome in neutrinos. What is the shape? So I don't want to look at the normalization because I'm not putting anything. So this is the shape of the neutrino flux if I put e to the minus 1.5, okay? What if I put, for instance, 2.4 as it was before? Can you guess what changes if also the proton is changing? So this choice increases basically. What are we doing if we are increasing the spectral index at the source? So if we have at the source a spectrum like e to the minus 1 in logarithmic scale, okay, let's say this is e to the minus 1. What if I have e to the minus 2? This will be much more inclined. So if at the end I want to have the same luminosity, it means that the integral of this let's call it Q, it has to be fixed because I want to power with this the measurements. So this L is fixed. So this means that in this case, in the case of the e to the minus 2, I will have that the ratio between the low energy particles and the high energy particles will be larger with respect to the case in which I have e to the minus 1. So if I have more low energy particles with respect to the high energy ones, this will have also an influence with the neutrinos. Because you know that the neutrinos carry the 5% of the energy of the primary proton. So if I have more protons at the lower energies, I will have also more neutrinos at the lower energies, which is what is roughly reported here. So the shape of the initial spectrum of the cosmic rays induces changes also in the spectrum that you expect of the other messengers, in this case of the neutrinos. So this is very important when you make some, so of course this, in this we assume that, in this case we have assumed that all the cosmic rays that we are seeing are just coming from a uniform distribution of sources and so on, which is probably is not a realistic case, because maybe there are sparse sources that give more, that are more intense than the uniform distribution. But anyway, just to have a simple scenario, if you take a uniform distribution of sources and you have your initial spectrum as a power law, then you compute the propagation and you obtain something that you normalize to the data. And this normalization is what you use to see what is the intensity at the source. So then you derive this as after you fit the normalization to the data. And this is the same normalization you have to use for the neutrino flux, so that you fix it, but also, but not just the normalization is important, it is important also the shape. Although in the case of the cosmogenic neutrinos, unfortunately we are much, so the expectations are much smaller than what is reported, than what is the sensitivity of the experiments like IceCube or also Auger. But anyway, this is a way to, for instance, try to do a multi-messenger study, so cosmic rays and neutrinos together, in order to, for instance, try to understand something about the cosmological evolution of the sources, which you could not understand only with the nuclei. Should look also to the cosmic ray, to the neutrinos. So this was more or less what I wanted to show, although maybe it's, I don't know, if it is overwhelming, if it is boring, this I don't know, but I'm still here in the next days, so if you are interested to know more details, it would be, to me, it's a pleasure to chat with you. The other option I wanted to show for, why it's doing like this. I don't know what is happening now. Oh, it's that does not respond, sorry. I wanted to show an option for the people who like to see what are the data. And this is a website in which is called the opendata.auger.org, in which the 10% of the real data of the Pierre Auger Observatory are released, with which you can do whatever you want. So you can look at the data set, you can visualize the events, and you can also analyze them, because it contains Python notebooks that you can run in the website, but you can also download them. So just for the fans of this visualization, you can choose, for instance, some details of the events, like, for instance, example events like the highest energy one, and then you can look how it looks like in the ground array, for instance. So that's what I was showing this morning. So in the ground array, this is depicted as something that is crossing some part of the array, and it is making a signal in these colored tanks. And the arrow indicates the direction, which should be this one. And the timing, so you see from green to red, green arrives first and then red. So you can play with this just to see. And these are the traces left in the stations, the ones which I was showing today. I mean, there are some examples. So you see this. in the 3 PMTs. All the stations have a name, as you can see here. And then there is also the reconstruction, which is the signal as a function of the distance for the activated tanks. So from the closer to, this is very close to the shower core, and this is very far. It's so you see, it's 3,000 meters. It's quite far. So it means it's, so if you remember, the tanks are 1.5 kilometers away from each other. And then you can also see if there is a 3D view, which is nice, I think. Work. So also for this, you can ask, I mean, or if you're interested, but this is a nice view of how the event is. So this is, I mean, of course, so it gives you an idea of how these tanks are invested by the signal. Or you can look also at the hybrid ones, right? The golden hybrid, which are the ones that have been seen both by the SD and the FD. And you can have the 3D view that in this case implies also that it is seen. You see, this means that a fluorescence telescope has seen this event. And I wanted to show the camera view. Yeah. So that means, so these are the 6 telescopes in one site. So there are 4 sites for the telescopes, and in one site you have 6 of them. And this is how the PMTs of the telescopes have been hit by the signal, which is going like this. It has highlighted the PMTs one after the other. So this you can experience yourself. You can choose the energy, the zenith angle, and so on. So I don't know if there are questions or curiosities about one of the or both the topics I have presented. Please. No, 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 it's not. I mean, this was released in February this year after a huge discussion within the collaboration, and it is only the 10% of the data. It's not the total, of course, but still with this you can, for instance, it's not just about the visualization of the, but it's also about the analysis. So you can look, for instance, at the energy spectrum. You can run it in your browser and see, for instance, how the spectrum changes if you change the exposure. So, I mean, of course, very basic things, but it's, I mean, if you're interested to see how the cosmic ray physics is realized then in these analysis tools, that is, I think, very interesting. And the interesting thing is that, I mean, it's not just about releasing the data. It's also about releasing the codes. So behind this, there is a huge work, of course, as you might understand, because what would you do if you had only the raw data? You don't know, I mean, how to start. Instead, in this case, you also have some notebooks, some analysis tools with which you can play at very levels. I mean, if you are an outreacher or if you are a scientist, you can play with this and see and maybe improve them and use them for your purposes. So, I don't know if there are other questions. But anyway, I'm here and I'm happy to join any kind of discussion if you want. From the more phenomenological, that maybe to, I mean, these analysis tools. So I'm jumping from one to the other because I'm still, I mean, as I was at your age, I still didn't decide what I want to do in the future. So I do both for the moment. You mean you mean the fit of the yeah, so I mean the flow is like I mean, let's try to explain that again. No, I mean, it's just because it was my last topic today, so probably this morning, so probably, so, no, it was probably, I was probably too fast. So we have one source that we then duplicate in the entire universe. So they are all the same. So at least this is one example of an astrophysical, very simple astrophysical scenario that we try to use to interpret the data. This source emits something like a spectrum. Actually, this is a sum depending on the mass. Do you see it? Or maybe I write a bit larger. So is a sum over the mass, because I produce a lot of masses. I want to produce everything. And then this is e to the minus gamma multiplied by some function which takes into account the maximum energy of every mass. Okay, so this is my hypothesis. So these are the parameters. The parameters are the spectral index, the cutoff energy, and the fraction of masses that I produce at the source. And this is my model. Then I have to propagate all of this. So in the end, I will have a J prime of E at the detection, let's say. And I have not just one, I have a lot of things. So we call this approach then with a propagation matrix. And then this, which is my expected flux, I compare to the data. And then basically I invent some kind of evaluation mode. So I will compare this to the data. And then I will find what are the best parameters that fit the data. And then at the end, I have an astrophysical scenario that tells me, okay, the sources emit e to the minus this, and they emit a lot of nitrogen. Okay? And of course, this has some quality, this fit, that I have to consider. And this tells me how good is my hypothesis on the astrophysical scenario, which is becoming more and more poor as soon as the data get better and better. So as soon as they have less statistical errors, which is what is happening. So our fit is getting worse and worse because the data are very small errors. So this is how you do it. I mean, you invent an hypothesis with some unknown parameters. Then in this case, there is propagation inside, in between, and then you compare to the data. And at the end, that's what it is. I mean, we find weird solutions in some cases, or disappointing, how to say, solutions that we try to interpret. Then that's our goal. I hope it was it answered your question. Yeah, sure. No.
Okay, hi again. It's Sunday, almost evening, so this will be light, okay? We will try to do something not too heavy, just trying to get a bit of experience how to retrieve the data. But I mean, I realize that for you, it has been a tough day, okay? So, first of all, please make small groups. Choose a pair or a couple of pairs with whom you want to work with, okay? And give yourself a name. You can name as you want, as a group, okay? So think a name that you would like to have, because we will have a competition, okay? So Yelena cannot help much because she's too experienced, so she will help me maybe. But yeah, don't help the others too much. And there is a gift for the groups that at the end will reply first to the final question, okay? Okay, so this is about data, you know why. And in order to look at gamma ray data or in general astronomical data, you have different ways. You have data centers, and here I put some examples. Maybe we look at them at the end if you have time. But the first one is in Strasbourg, is the Centre de Données de Strasbourg, and it's where all the astronomical data are collected from over the world. Okay, so if you can find there even optical data, infrared data, microwave, up to high energy gamma rays. But the point is that, especially for gamma ray data, these data centers are not complete. So you are not sure, if you don't find data there, that there are no data about that source. Maybe they are not loaded because we are not still fully synchronized with these data centers, but we are starting to be. So in the future, we will put all our data as well in this databases, so that if you want all the data ever collected from a region of the sky, you can really download all this kind of data. Then you have the database from NASA missions, and another one in Italy from in general space missions all over the world. And then you have catalogs. Catalogs are different from generical data, because in catalogs usually you collect all what you have done up to that moment, okay? Probably in a catalog you don't have the result of a single observation campaign from a source, but as Fermi did in the Fermi catalogs, you have the result of the analysis of all the 9 years, the first year, then the third year, then the fifth, and the ninth year. So usually in catalogs you have a list of sources and all the photons collected from the sources, and usually the paper of a catalog is very short, because it points to the catalog that is an enormous table with all kind of informations. But if you read the catalog and the table header, you can usually somehow understand and find what you need. Okay, so and then in this catalog thing, there is this effort, the TEV catalog, that is trying to collect not really the data, but the sources that have been detected at TEV. So the first small exercise that I propose you, while I come into your table and you tell me the name of your team, so we know who will be the winning team at the end, is to build a spectral energy distribution using one of these databases. So you can easily do that with the online tools freely available. I think I shared with you the slides with the Telegram channel, because I had no other way, sorry. I was not fast enough to upload in Indico, sorry. So you have the links, so you don't have to copy paste the web. So the point here is to go to this database and try to build an SED. You will see that in the tab of the database, you have different sections, and you also have tools Tell me, okay, if you are there in the web page. Yes? So go to Tools, and at the bottom of the list, you see SED Builder. SED Builder, you enter there, and you put the name of a source. I suggest, for example, the neutrino blazer, but you can choose the source that you like. The neutrino blazer name is TXS0506 plus 0656, but as you start typing, it completes itself because a lot of people started to do that. So in the name, you start typing TXS0506 and you should find the source. You click on the name and you go to Build SED. And it should open a page with axis, but an empty plot, right? You have to load the data. So click Load the Data. And like that, you will load all the data available to this database. Careful. This is not all available ever published. This is what was uploaded to this database. And if your connection is fast enough, not like mine, you will see an SED of the source. Can you see it? Yes, no? Have you loaded the data? Loading, okay. And at that point, you will see what I show you, the so-called archival data of the spectral energy distribution that you always see from us. What's your name? Of the team? Have you chosen a name? You can think. Does it work?
Yeah. Is it this?
Yes.
Great.
Okay. You can see clearly that it is the SED. Have you selected a name? Did you? Okay. So they are there. First ones. Okay. No. So you did a mistake. So go back. Because sometimes you close it and put it, delete that. Type TXS space. Sometimes, yeah. Space. Try like.
But then this is just the same one.
Try again, because it's a bit silly sometimes. Let's see. You should have a lot of data.
Yes. No, I'll wait for it and then.
Try load. Why?
I don't know. We did exactly this, but then click one.
That's weird because they have all the points.
No.
Okay. Oh. So experimental factor, try always 2 times because sometimes the databases are not well connected. Are you there? Loading. Try to change the network. I don't know. So you should be more or less there. You have done your first SED probably. And this, as I was saying before, are the usual archival data, the ones that we download, and then we plot on top of them our data. This is a nice, an extremely useful tool because in this database from ASI, you can find a lot of data of blazars, especially that is mostly devoted to blazars, and you can play. If you see on the right, it is an old-fashioned looking page, but still you have a lot of options to make your plot different, change the scale, change the color, and especially what is important, select the data that you want to plot, because now you have selected all the available data, but you can expand the data part and you see which are all the data that you are plotting. You can select and unselect instruments data. Sometimes, for example, optical data are not properly analyzed once in the databases, so you want to remove them because they make a lot of noise in your SEDs and things like that. So by clicking, you can remove data, and once you're happy of the data that you have selected, you can download everything. How can you download the data? You look carefully. You will find something like, I don't remember, export, and you choose if you want, how you want to, as a comment option, and if you want a logarithmic or a linear scale. And then you download your ASCII file. Did you manage? What you want, it's just an exercise. It depends on you. No. In this case, all these data are okay. It's just an exercise. We are not using this data. No. Just remove the optical because there are always too many data in the optical. And you download and then try to open the file. It's, again, not very user-friendly, but you can get easily used to that. And you see that you have many lines, and in all the line, you have an entry with the catalog data. Okay, so you have already downloaded your first set of data. From there, you could, for example, build an SED, try to fit with your own code. You can build, for example, a Python notebook, and then you take this data and you plot them, and then you try to fit if you want to fit, for example. This is the first example that I would like to show you. Are you all there? Okay, so let's go on now. Let's now change catalog. And I ask you, how many TeV blazar do we have in the sky? The answer is hidden in the TeV catalog. So go there, TevCat 2. There you have a list of all the sources detected by Cherenkov instruments. But then you have to select the blazars. Think how to do that and try. First of all, how many sources do we have exactly? To see the number of entries of that table, you have to go to the bottom of the table. Who is the first one? Number of sources in total before filtering? You are not valid. I see that you found the answer. You too. Did you find the answer? Ah, you found already. Ah, you don't have internet? Very good. Yes. Excellent. Tomislav, don't help too much. Blazar, perfect. So how many sources do you have as a blazar? But first, please remove the filter and tell me how many sources in total do we have? $247. And now the blazar only BLZ filter I saw that you found them. It's 79, right? Were you able to solve the connection issue? Finally, good. So this is the TV catalog. These are the 79 sources that were associated with a blazer and emitting a TV. Now, what is this catalog useful? It doesn't give you yet, or it will never do, I don't think so, the data. But it's useful because it gives you all the publications related to high energy astrophysics. So for example, select again one source of those, TXS for simplicity, TXS 0506. If you click on it, you see that you enter a list of informations from TV observations on that source, and all the papers related to TV data. Please raise your hand if you did that. Great. Great. So now go back. Try to answer this question. How many of these TV blazers do have uncertain redshift? So there is not a flag for uncertain, but try to think about it. These are blazers, they are extragalactic. They cannot have zero redshift, okay? So what is flagged 0 means undefined redshift. So you can try to order the table. One sweet is for you. 10, great. So you can move on. Try to answer this second question. Now we want to know how many Fermi blazers do we have. And unfortunately, we do not have such an easy list, so you should check the paper. Have you found how to order the redshift? Don't worry, I can blazer, and then you have only the blazer listed. Go on the bottom, and you see 79 sources. Okay, because automatically when you put a filter, it chooses. You can see that from the map. That if you remove it, immediately you have all the sources popping up. And now order according to the redshift distance. There is, if you click there, on the other, re-click. You should have all 0, 0, 0, 0, and these are the uncertain ones. They should be 10. Okay. Have you found the?
Yeah.
How many uncertain redshift?
Uncertain. No.
Yeah. No.
No.
Try again. Far away still.
Doesn't put the zero or anything. It isn't.
Which one?
Yes.
Okay. In my case, I had some 0. Oh, yeah.
There are some which have 0.
Then it's more.
Yes.
Then it's more. 14.
Which no 5, right?
It's both 0 or empty field. Sorry, I didn't realize that. So it's 14. Let's say so. Okay, now we are already at the other question. So you have realized that more or less we have tens of blazars at TV and a good fraction, let's say 10% has uncertain redshift. And now let's see instead how many Fermi blazars do we have. And to do so, I was telling them, look at the, you already have the answer in principle in the abstract of this paper. So it's easy. But that, so do you know how many Fermi blazars we have? Who knows? Give me the number. The 5,000 are all the Fermi sources, but the blazars is a subset. There is not the number in the paper. Yes. $3,137 Lat blazar is the number. 3,000 over a total of 5,000 sources detected by Lat. So it's more than 50%. Okay. Okay, good. So you see, there is not an easy, a unique way to access information and data. You have to know a bit and take some time, but a good idea is starting probably from the publication and knowing some basic sites like the TV that helps you a lot to see all the papers published on a subject. Now let's go to the real exercise I would like to give you. This is not trivial. In principle, it's trivial, but then you extracting informations might be difficult if you do not know very well the tools. The only thing that you need is a software that reads FITS files. If you search Google, it will tell you, well, GIMP reads FITS file. Yeah, but it doesn't read tables, or at least I wasn't able to do that. So usually what I use, I follow the NASA prescription, and I use a software that is called FV, FITS Viewer. It should be very easy to install. If you click on that link, you can try, so that then you can do the exercise. The exercise is this one. Download the TV data, the real data from the publication. These are these data points. You will have both spectra, and I ask you to extract the EBL absorption factor by the comparison of the two spectra. It's just a formula. We can write it down later, but first you have to be able to read this FIT file. So try to do that with this software. Does it work? I see that you are searching for the file, right? So it is, look for the blazar name, QSO B02, with Control F, and you will find, if you put 0 to 18, okay, if this, there is only one publication on that source, so you have there the link to the feeds file in which you have the data. Bravi. So which file did you download? This one? 0 to 18? No, because in the other one you don't have the absorbed spectrum. So try to find 0 to 18. This is the gravitationally lensed blazar that we saw this morning. I'm sorry that everything needs software. So if you need help, ask me. I'm here for that. Ah, bravo. Every time you have to do the paths in your laptop. I'm sorry. I can give you my laptop if you want. So, have you downloaded the software?
Yes,
No, it's okay like that. Now you have to find in your laptop, devi trovare nel tuo computer. Chiudi, è old style. Devi andare su questo, sei in una directory che ha deciso. No, su quello prima. Fai open file, this one. The double, sì, clicca 2 volte e tu stai andando indietro nel tuo computer ancora finché non arrivi a dove l'hai scaricato, sul desktop il file. So, ancora indietro. No, ok, users. Fai Windows maybe. Forse c'è desktop qua. Senza users. Oppure Facebook? È qui che hai messo. No, questo è proprio il programma. Ok, loro ce l'hanno fatta. Posso aiutarvi? Allora, avete aperto, you open the file.
yes.
And now this is a fit file. Open here the corner. Okay. In a fit file, you have different entries.
Okay.
Each of it is usually a spectrum or a map.
Okay.
And then you have an header of the file that is the first thing that you want to read. For example, spectrum, you want to read the header to know what is inside the file. So click here. No, just click there, header. And it is telling you, here, this file is the observed spectrum for redshift, blah, blah. So the observed one. Now try spectrum 1 then. What will be the absorbed spectrum. Okay, so these are the 2 things that you want to know. And now you need the data. And it is in all, not plot, all. All gives you the data point. Okay. So now you have your data points. How you extract what is tau? Ok, li avete plottati. Instead, you want to know the data. So you can read the header of each of the 2 files. Spectrum. Spectrum is the observed spectrum. Well, spectrum 1 is another thing, is the absorbed spectrum. So you can compare the 2 Ah, wait, and now the data. Close there, and you go to all. You access the table with the data and what is. So remember, this is the gulp that I give you, but you don't see from there that the relation between the observed and emitted spectrum is observed spectrum is the emitted spectrum multiplied by E to the power of minus tau. I am asking you tau for the 3 points, the 3 spectral points. What is tau from the data that you have? It's really easy now that you have the data. Try to think. So in the header, you know what is that file. For example, spectrum is the observed spectrum.
Ah, okay.
While if you open spectrum_1, that is the absorbed one.
Plot, for example,
No, no, plot,
okay.
no. Header, the absorbed. So now to extract this information, the easiest thing is to look at the data and do your math. And the data you can access clicking all.
Okay.
Fantastic, very good. Now header tells you information about not theta square. Look at the spectrum. Spectrum, the one below. So this file is related to the observed spectrum. While click, for example, spectrum 1, that is the deabsorbed spectrum, the one corrected by EBL. So these files, and now the data are in all. All?
Wait forever? Okay.
These are the data for the deabsorbed spectrum. And if you click all on the other one, are the data on the observed one. Try to compare the numbers if it is not the slope, the tau. No, it's not the slope. Pink. Observed, intrinsic, deabsorbed. They are simply related by E to the minus tau. How do you estimate E to the minus tau and therefore tau? That's all. I will stop here.
No, the only point, so they have to fit them, or do they?
No, I asked them to estimate tau.
Yes.
And that's it.
Point or
Yes.
From the point?
Yes. For each point, tau. You can estimate tau to see the dependence with the energy, and that's it. No, I will not go into fitting procedures. That's enough. Just, it's okay, I think. They will follow me already happy.
Yeah, everybody's working.
Yeah, because there is a price. Don't look.
What is it?
No, it's not a beer. It was unprofessional. So tell me if you need help. Scusa? Non apri il file con Fit Viewer? Ma io faccio senza Open, Fit Viewer e clicco. Prova FV, spazio. O forse devi... Oppure clicchi su Fit Viewer nel Mac e poi lui ti fa andare col suo tab a prendere il file. Clicca. Ah no, allora no. Ah, mi spiace. Yeah.
What is the observer, not the flux, the flux, no?
Depends on the file that you opened. Which one is this? Which tab is that? Ah, sorry, I didn't say. So the first one, go to header. and it tells you what is that. This is the observed spectrum. While if you go on the header, the other, you will see that that is the deabsorbed. So always look at the header that is telling you what is plotted. So what is tau? Yes, for the first point. Yes, of course. Are you getting closer?